Hey everyone, welcome to our event. Uh, just to introduce our organization, I think some non-members signed up. So we are Tau Beta Pi, an engineering honor society that recognizes all engineering majors with high academic achievement. And so we are an invitation only honor society because of that academic requirement. So if you do end up getting an email from us at any point, definitely keep that in mind. Definitely consider joining us. And so I will thank you to Nicole. I am the president of Tau Beta Pi. Thank you to Nicole, next year's recording secretary, for organizing this event. And thank you also to Dr. Reuter, Matt, for coming and giving this workshop for us. So I will pass it off to him.
All right, well, thank you very much. And I appreciate the opportunity to be here. I'm glad to see all of you, or at least all of your avatars or your initials as the Zoom bar may be. For those of you who don't know me, my name is Matt Reuter. I am a teaching professor in the Applied Math and Statistics Department, as well as the Institute for Advanced Computational Science. In recent years, I've been predominantly teaching 3 classes, AMS 103, an SBC course for non-STEM majors, looking at technology and math, which is a lot of fun. I've been teaching Calc 3 for a good amount of time now, and sort of on a more ad hoc or on and off basis, AMS 510 for graduate students looking at linear algebra and advanced calculus. So about me, I am obviously on faculty. I've been doing research, although not as much presently. I've been focused more on teaching efforts lately. But in areas, my PhD's in theoretical and computational chemistry, which has a huge amount of mathematical analysis and linear algebra and matrix gunk going on underneath, which I would be happy to talk to any of you about at some point, although that won't be our main focus today. And so instead, what we're going to do is talk about different pieces of software and look specifically at Mathematica and what it can do, how we can use it. This is half intended to be a tutorial, half intended to be an example, and half intended to be, what do you want to see out of it? So please, I'm perfectly content if you want to go to the reactions bar, raise your hand if you've got a question. That way we just don't all end up talking on top of each other. I'm also perfectly capable and willing and happy if you want to just type questions into the chat bar. And I will try to respond to them as best as I can. I probably won't actually type the response, I'll just talk it, but those are great ways to communicate with me and to ask questions at any time during this. And so if I'm correct, then that means we've got half tutorial, half examples, and half what do you want to see, which means this is 150%, which means you're getting more than you paid for. All right. So what I want to start with is just to overview, when Nicole approached me first about doing this, the idea of this talk was maybe to be sort of an introduction to Mathematica and MATLAB. So maybe just for me to get a sense of where everyone's at here, if you go to the participants, sorry, not the participants, but the reactions bar on the bottom of your Zoom window, you'll see there's the yes and no things. How many of you click yes? Have you used Mathematica before? I'm just sort of curious what the numbers are. All right, I'm not actually, that's right, I'm not host. I don't think I'm actually able to see the numbers. Okay, so I'm seeing some people with thumbs up signs. Okay, great. So some people have, some people haven't, that's fine. I'm guessing if we went the other way, so there's another software tool called MATLAB. Who's used MATLAB before? Okay, I'm seeing lots of thumbs up now in the participants bar. So this is not terribly surprising to me. I will start by making a confession. Seeing as we're in the midst of all the religious holidays right now, I'll make a confession. I have never used MATLAB. So you can think less of me if you will. I think less of myself every day for that fact, yet I don't ever bother going to change it. And part of that is because of the nature of the research that I do. Part of that is just out of necessity. But the big thing is, a lot of times people think Mathematica and MATLAB are interchangeable pieces of software, that they both are sort of like, they sound like how they have math in them because Mathematica and MATLAB, and these are like the same thing. And it turns out that Mathematica and MATLAB are actually two very distinct pieces of software, not just because one is made by Wolfram, named after Stephen Wolfram, that's Mathematica, and one is made by MathWorks, which is largely Cleve Moeller doing MATLAB, which are two completely different companies. But they were actually designed to do two different things entirely. And so if you're wondering, which one should you use, it really does depend on what are you trying to do. They do share a lot of common functionality. So things, that you can do in Mathematica, you can do in MATLAB. Things that you can do in MATLAB, you probably can do in Mathematica. The issue that you might want to ask yourself, or the question in the back of your head is, why would I want to do that? And so what will end up happening is something that Mathematica was designed to do and will do very well, MATLAB can do, but maybe very slowly or very inefficiently. Likewise, certain things that MATLAB was designed to do, Mathematica can do, but much more inefficiently. Okay, so you would probably want to do that in MATLAB. And the distinction between the two, yeah, I noticed there's some comments here. Yes, so like Fortran and C++ are hardcore languages. Yes, only you can just draw a line through Fortran, because death to that. Sorry, by the way, part of this talk, you get my unfiltered opinions. I despise Fortran. I had a 6-week scholarship a little over 10 years ago for some study abroad stuff. And rather than actually doing the chemistry, I spent the entire 6 weeks debugging an issue in Fortran that the C++ compiler would have found. So I have, and that's just one instance of my experience with Fortran, death to Fortran. I'd rather have COBOL, and that's a dated reference. Okay, so anyway, to keep in mind, so what were Mathematica and MATLAB designed to do? Does anybody know? I mean, I'll do this if you want to put in there. So maybe if you've used MATLAB before, we'll start there since most of you have. What was MATLAB actually originally designed to do? If you want to maybe talk about it in the chat bar. Yeah, so Oliver, you're hitting the nail right on the head. Basically, Mathematica, it doesn't really answer the question that I posed, it answers the complementary one. Mathematica was designed to be what's called a computer algebra system, or a CAS, which is to say it's a way of doing a lot of algebra in the computer. So think back to like when you were in high school and your teacher said, here's a big polynomial and you need to factor it to find all the roots. And you spent all the time factoring that goddamn polynomial. And you spent so much time on this, and yet then you felt kind of accomplished when you were done, until you then got to calculus and realized, oh, well, all I need is really root finding, because what I really want to do is find, maxes and mins of things. And then you get to multivariable calculus and realize, oh my God, it's a system of equations that I need to find the roots for, because I want to know maxes and mins of even more complicated things. And you sort of built on this. And how much time then, as you started getting into calculus and linear algebra and multivariable calculus and probability and statistics, how much time did you actually spend doing calculus and linear algebra? And how much time did you spend just doing tedious high school algebra? We just had the quiz last week in my multivariable calculus class on optimization problems, where it's, oh my God, take like 3 derivatives and then spend 35 minutes doing algebra to do this. So, this is what Mathematica was designed to do, because I imagine I'm representative of most human beings, and that when I'm doing algebra, I make all sorts of careless errors. And so instead of getting the right answer, I get a horrifically wrong answer, not because I did, the calculus wrong or the setup wrong, but because 2 + 2 is 5, which it's not most days of the week. I realize it's April Fool's Day, so maybe today 2 + 2 is equal to 5. But generally it's not. And so Mathematica was designed as a computer algebra system to help do a lot of those algebraic operations. How do you do like factoring polynomials? How do you find roots? And how can you do all of these operations in a more robust way? And so it was designed to manipulate, yes, thanks, Ian. Designed to manipulate expressions. And then once they had that built out, so how do you now think about making computers add different algebraic expressions or subtract or multiply. And this gets into a whole tree structure where those of you that are more interested in computer science and computer programming is actually fascinating discussions. I've got some books either in my other room here or in the office that I haven't been to in a year that talk about some of these topics. And it's really interesting to see how they work underneath the hood. But that's what Mathematica was designed to do. And then once they had that and this tool for doing algebra, they found they could build on other operations like, oh, well, once we know how to deal with functions in an abstract sense, not necessarily like abstract algebra, but computationally, like what is X? Well, X is just some independent variable. We can think about, well, what could we do derivatives? And so they were able to program differentiation in. Well, and if we can do derivatives, you know what would be also really cool to do? Integrals. And so they started building in all of these tools, and over the decades, you now get Mathematica, which is this really powerful tool for doing all sorts of symbolic operations and looking at how do you work with these algebraic entities and do certain things with them. And we'll look at some examples here in a little bit. Contrastingly, MATLAB was not designed as a computer algebra system. So as has been noticed, there is this package called Symbolic, which was sort of an add-on effect into MATLAB, but that's not what MATLAB was originally designed to do. MATLAB was designed to do matrix analysis and to do matrix computations. As I recall, MATLAB is a portmanteau of matrix laboratory. I could be wrong on that. I've never used MATLAB. Keep that in mind. And so, you know, that's what it was designed to do, was to do a whole lot of like matrix analysis. So looking at matrix vector computations, doing matrix multiplication, looking at properties of matrices, so things like eigenvalues, eigenvectors, singular values, doing different decompositions like the QR decomposition, LU decomposition, and so on and so forth. Which is to say, MATLAB was really developed to be a numerical powerhouse. And so to not only take these matrices and be able to do those operations, but to do them efficiently, okay? And so when you want to then do numerical analysis, you've got a matrix and you need to factor it, you want to know its eigenvalues, you want to know whatever the thing is, and numerical answers are sufficient. MATLAB is one of the best pieces of software out there for you to use, which is one of the reasons it's so popular and so ubiquitous. But that's, again, keep in mind, 30 years ago, that's what it was designed to do. So the fact that it's become so good at that is cool. Go engineers. All right. And so, but keep in mind, that's not what Mathematica was designed to do. Mathematica was designed to be more of a symbolic engine. MATLAB is a numerical engine. Now, over the 30 years, they then realized they could build on, once they have this framework, they can start to do symbolic things, and having a certain amount of symbolic functionality in MATLAB would be beneficial. And so they added in the symbolic framework. And so you can do symbolic work in MATLAB. But okay, Oliver, it looks like I'm picking on you because you spoke up early in the chat bar. You've used symbolic in MATLAB and you notice that it's not as robust as Mathematica. It feels, when I've talked to other people that have used it before, it feels like a bit of an afterthought. Like it's there and it's usable, but it's not necessarily the most natural thing or the easiest thing to use. Do you have any other comments on that, having used, or if anyone else has used symbolic in MATLAB?
Yeah, that's correct. I think MATLAB originally licensed Maple's sort of tools, and then it later, I guess, hired some programmers to write their own toolbox. In our group, we sometimes, for example, have to solve systems of hundreds of polynomials, and MATLAB just completely fails at that, whereas Mathematica can actually handle it.
Right. Yeah, and so that's, thanks. So, and by the way, so Maple is mentioned. Maple is sort of a competitor to these, where Maple, it's more of a computer algebra system in the guise of Mathematica, but it was actually sort of developed to be sort of as a middle ground between the two. And so it's not as good as Mathematica on the computer algebra system, and it's not as good as MATLAB on the numerics, but it sort of straddles the fence. Yeah, so again, so like MATLAB has the functionality for doing symbolic work, but it's not great. It's a similar thing in Mathematica, where if you want to do numerical work in Mathematica, you most certainly can. But you're sometimes kludging it in. it doesn't necessarily feel unnatural to me doing numerical work in Mathematica, and I've certainly done it plenty of times. The issue now is not so much that it's sort of weird to use, it's that Mathematica is so slow. It's designed for doing symbolic computations. And so if you're actually wanting to do anything numerical and speed is of the essence, don't use Mathematica. For the love of God, don't use Mathematica. It will just grind your computer to a halt and just take forever. So it's actually easy to program in. It doesn't feel like it's kludged in, because certainly if you can do something symbolically, you can absolutely just put numerical values in there. Just the issue is it's not what Mathematica was designed to do. And so there's all these other bells and whistles and cup holders and airbags built in. It's the DeLorean when all you needed was a car. Who needs the flux capacitor? We don't need time travel. I just need to get to the grocery store. And today is fine, not tomorrow, not yesterday, today. Okay, so that sort of is the base approach. So when you're looking at sort of which software do you want to use, keep in mind, what are you trying to do? If you're looking to do sort of symbolic work, Mathematica is a really great piece of software. If you're looking for more numerical work, MATLAB is probably the better choice. But beyond that, I just wanted to sort of give that little overview. Does anybody have any questions sort of then about that history or sort of what those software packages were designed to do before I'm going to screen share and we can start doing a little bit of like a tutorial and start looking at some examples of Mathematica and see how some of the stuff works? Like I said, I do have some notes prepared and I've got some examples prepped, but I'm also perfectly happy to take questions and ideas from you and see if you want to try to like stump me on the spot. All right, well, I'm not seeing anything. So let me do a screen share here. So we will pull up a Mathematica notebook. So of course, we've got this big Mathematica notebook, which is right now just a blank page. We'll start putting things on here. Everyone can see it okay? I just want to make sure everything's good. All right. So, I mean, the biggest thing in Mathematica, and the biggest piece of advice that I can give you, and if anyone's used Mathematica before, feel free to chime in and either tell me I'm an idiot or confirm that I'm not an idiot in this case. Learning to use Mathematica isn't so much as learning how to program in Mathematica, because Mathematica is in a sense its own programming language. It's, if you're familiar with types of programming languages, it's usually regarded as a functional programming language. Something in the lines of sort of along the style of Lisp, more than C++ or Fortran or any object-oriented or procedural language, although you can do those things in Mathematica. But learning to program Mathematica isn't so much as learning the syntax and learning how to use it, so much as realizing Mathematica is a spoiled brat and rephrasing your question so that it becomes the question Mathematica wants to answer. And that just requires a bit of practice. So some of the big things about Mathematica is that it structures most everything in terms of lists. And so when you're going to work with lists, everything is always done with curly braces. Is the font size good, or should I make it a little bit larger? Can people see this okay? Okay. Thanks for the feedback. So basically, Mathematica uses like curly braces to indicate lists. And we'll see as we start looking through some examples here, there's all sorts of things, like when you do a lot of the functions that it's going to do, even for sort of standard things, it's going to return things in list format. And so getting used to processing lists becomes a really important thing. And so, we can think about having a list. We've got, like here's A, B, and C. If you're wanting to follow along at home, you type it in to evaluate. You hold Shift and hit Enter to evaluate. And notice Mathematica will give you sort of, here's this input. This is the 39th thing, because I haven't cleared out my kernel recently. I was making examples and testing things before we started this meeting. And it also assigns it an output. So if we ever wanted to know this list in Mathematica and we didn't actually assign it a name, because of course we could always say make list equals ABC. Well, now we can refer to it by the name list. Otherwise, we could always go back and refer to it as like out of 40. And so then the other thing that this exposes then is that square brackets. So curly brackets tell us lists. Square brackets tell Mathematica is a function evaluation. So anytime you see square brackets like this, it's meaning there's some sort of function or procedure going on along the way. So like out would be a function, and then 40 is your argument to it. It's saying what's the 40th thing in this out function, and we could go in and see, well, out of 40, and it gives us our list of ABC, just as a shorthand. Other thing to keep in mind in Mathematica, anyone who's really adept at Mathematica will know there's a shorthand for doing everything, because Stephen Wolfram was apparently a big fan of Perl. And why have one or two simple ways of doing things when you can have 50 equivalent ways that are completely unreadable if you're used to a different one? So we're not going to get into all of that. But if you ever look at someone doing hardcore Mathematica programming and wondering why are there random pound signs and percent signs and at signs and what's going on, it's someone's being cute. We're not going to get into that today. And so it's sort of a functional programming thing. And so we can start to see, what's going on by looking at what are some of these functions. So, one thing that we can do, think of it, it's a computer algebra system, is, maybe we didn't want to factor, but we had some polynomial where it was already factored. And we can just, say we want to expand that out. Okay. And so you can go in there, these built-in functions like expand, you can type it whatever it is, and it's, goes and it just multiplies all that out for you. I know this is a really trivial example, but this shows sort of the power behind what's going on, where we haven't specified what X is. It's just some unknown, and Mathematica is doing that algebra for us. Okay. Other thing to note, and this is how I think of using Mathematica. This is how I use Mathematica. Once you've got these functions, and we'll look over some basic ones like expand, you'll notice there's this little, like the info get help. If you click that, it will bring up in a different window. So let me switch over to that. We'll flip back to the other notebook here in a moment. These Mathematica files are called notebooks. Mathematica actually has a phenomenally well-developed documentation system inside it. And so whenever you're wanting to look at these functions, the biggest piece of advice I can give you beyond some of the basic ones is either if you like computer science initialisms, RTFM is really, really useful with Mathematica for read the manual. Also LMGTFY, has anybody seen LMGTFY as the initialism before? I'm seeing sort of no's from people. Let me Google that for you. You can find there's actually a lot of really great Mathematica resources available online. There's a whole Stack Exchange forum for it that has a lot of really good examples and a lot of really clever people on it. And so even when I get into weird issues of how would this weird thing work in Mathematica, Google a couple keywords, and usually within 2 or 3 Stack Exchange posts, I can find something that usually gets me what I'm looking for. And so I can't recommend those resources enough when you're learning Mathematica, or even when you know it and are looking for, how do I do sort of this weird kind of thing that actually turns out to not be that weird, but why do I have to Google this? There's stuff out there. And so you can look at expand, and so you can see sort of, it shows you, more or less what's going on, details and options. This is a pretty simple function, so there's not a lot to see. But then coming over, it'll give you some basic examples here. So like expand x1 plus x to the 10th power. And so it's going on a whole bunch of other things. Neat examples are sometimes fun to look at. It'll show these. So like here, as I tell my Calc 3 class, you can call variables whatever you want. So here they actually, called their variables smiley face and frowny face. And so if you wanted to know what is smiley face plus frowny face to the 5th power, there you go. They're just symbols. That's what computer algebra systems do. For those of you that are masochistic and want to know 1 plus x, I'm not sure that really counts as a neat example, but look, we can do things brute force. You can do all sorts of things. So here's more sort of like list processing, where there's all sorts of weird list stuff going on. And then it usually gives you a whole bunch of other related functions, if you're so interested, and you can click on those and see what's going on. Another one, I think it's got it listed here. Yeah, so then factor, going back, we mentioned before, if you actually wanted to factor a polynomial, so you were given that expanded thing and wanted to factor it, you can go the other way around by saying factor. This one's got a little bit more meat to it. And so there's a little bit more sort of, what are you going? Do you want to do it over, integers? Do you want to do it over reals? You can specify all sorts of other options and again, see if there are some neat examples, and actually start showing you we can plot things because why not? There's neat stuff built in there. All right, so we'll flip back over to our ongoing one and hold on, now I'm lost on my desktop. There we are. All right, so that's basically, you know, sort of a base introduction. So we've got, you know, there's our function name, we've got the square bracket telling us that's it's a function call. Normal parentheses are just again used for order of operations in the normal sense, and then we haven't really seen anything with lists yet. So if we wanted to take this, a couple other operations just for base functionality, we want to do like derivatives and integrals. It's very straightforward to do. Derivatives, you would think it would be actually derivative, but they shorthanded it. It's just capital D is the name of the function. So if we wanted to take our function from above, so we get 15 plus 2x minus 16x squared minus 2x cubed plus x to the fourth. We can differentiate that. And if we were to just do this, notice nothing happened. Anybody want to take a guess why nothing actually happened? Because I'm pretty sure 15 plus 2x minus 16x squared minus 2x cubed plus x to the fourth is not the derivative of itself. I do not believe this is an eigenfunction of D. You want to take a guess what the issue is?
Maybe we didn't tell it what variable to take the derivative with respect to.
Exactly. Mathematica will not assume, even though there's only the one variable appearing in this expression, it's x, Mathematica will not implicitly assume. Again, Mathematica is a spoiled brat, and it does not, in some sense, it's a good thing. In some senses, it makes you go bald because you pull all of your hair out. We didn't do it. So if we want to differentiate with respect to y, now naturally, so we come in, we add a comma, another argument, say y, and naturally that derivative is 0. More interestingly would be the derivative with respect to x, and we now see we get our 2 minus 32x minus 6x squared plus 4x cubed, and so on and so forth. If we want to do higher derivatives, you can just sort of keep tacking on as one way to do this. Of course, you can change variables up there. In this case, it will zero it out. You can also sort of lump together, if you wanted to know just the second derivative with respect to x twice. You know, there's different shorthand ways to do all sorts of these things, but you can end up doing derivatives pretty straightforwardly. You can also do integrals pretty straightforwardly. We didn't get all cheeky, and integrate is not just I, it's actually integrate, but we can plug in, I don't know, what's our favorite function? Let's do sine of x squared. And, you know, just as before, notice now here, if we just do the close, it doesn't even try to evaluate it. It says, oh, there's too few arguments. Okay, so we can specify what the variable is. And so if we integrate with respect to x, then we get our x over 2 minus 1/4 sine of 2x. It actually tried to do some simplification. And so in that sense, we can do anti-derivatives by just leaving it as sort of a free variable. If we wanted to do a definite integral, or let's say x goes from 0 to 1, we can do that too. Specifying, you know, integrate with respect to x, lower bound is 0, upper bound is 1. And now we actually get analytically what that value is going to be. All right, and so in this case, it's 1/4 2 minus the sine of 2. If you wanted to just get a numerical value, there's a couple things you can do at any time in Mathematica. If you've gotten rid of all of your variables and you just want numerics, you can always do / capital N to give you a numerical value at the end. And so in this case, it's a little over 1/4. When it comes specifically to the integrate function, there's also a related function called nintegrate, all one word there, which basically says don't even bother trying to do it symbolically, just go ahead and do it numerically. This is a simple enough integral that it runs pretty quickly, but just be warned, that function can be really, really slow. Versus even if you had like a numerical value here inside integrate, it would try to do it symbolically as far as it can. And then it would only go to numerics if you actually introduce something along the way. So like if you said like 1 point times x. So the moment you add that decimal point there, you're giving Mathematica license to go numerical, even though it will try not to. Notice that's now there, versus if we had just 1x, it'll keep things symbolic. So that's also another hack for how you can get numerical values if you really wanted to. Any questions so far? I know we haven't done anything super sophisticated yet. We have to learn how to walk before we crawl. All right. So to me, one of the biggest uses that I find Mathematica nice for, besides just sort of being a sanity check when I have, algebra that I'm pretty sure I would screw up on my own, is that it is a really nice tool for doing plotting and actually getting visualizations of data. And Mathematica can do a lot. The good news is there's a lot it can do. The bad news is that means you've got a lot of options, which means there's just enough rope to hang yourself with. And so, if we want to actually plot a function, if we're thinking just sort of like a function of one variable, so let's actually maybe look at our 2 minus, what do we have? Sine of 2x. Sorry, let's go back and get this as a function. There we go. So we have our x over 2 minus sine of 2x over 4. Let's see what's going on there. We can always plot that. Again, so we specify what's the function that we're plotting, and in the other one, so then what's our variable and what are the bounds of the plot. So x goes from 0 to 1, and sure enough, we can get something like that. That's not super interesting, so we can change our upper bound to maybe 2 pi, and we can see we've got a little bit more shaping going on. Again, all sorts of options inside plot. This would be a good one. I apologize for sort of the whiplash here on the videos, but I'm going to pull up the screen, the help screen here, just to sort of show you what's going on. This one's got a little bit more meat to it. For graphics, where there's all sorts of different ways to go about plotting. If you want to do multiple functions, you can do that by just making a list of the functions that you want to plot. There are all sorts of other weird things. You can actually specify regions in which you want to plot and sort of restrict what are the x values, and Mathematica has got some really clever and sometimes not so clever ways of doing that. But when it comes to graphics is where now the details and the options become just like mind-blowing, and this is where the documentation becomes really, really quite helpful. And so, you can see different examples. So here's where regions can come up, and you can actually sort of like cut and splice different things together. All sorts of different labelings that you can do. You can actually make your graphics interactive with things like tooltips. You can change styles. You can add hyperlinks if you wanted to. So you can actually take these Mathematica notebooks and you can package them up. Mathematica, always being willing to make its own format for doing special things, made a PDF analog called a CDF, which I think stood for computable document format. So you could turn like your Mathematica notebook into an actual computable document and distribute it. People can't write their own Mathematica code, but you could then like run examples, put in things like tooltips, hyperlinks, and animations and things that people could run those like they would look at a PDF document using a free viewer that Wolfram would just happen to make available to you. All sorts of other options for how you want your graphs to look. You can change, the aspect ratio of the plot. Do you want axes? Do you want it to be actually framed? Are there any weird points where there might be discontinuities or singularities that you might want it to be aware of? How big is the mesh that you're going to go? What's the performance goal? Do you want legends? How many points should you be looking at? Do you want to change the style in which it's plotted? So you can change the colors, you can change the dashing, you can change the thickness. All sorts. It gives you, there's a bunch of examples here, sort of neat things. You can see different thickness. Basic examples are fun. Again, you can do filling depending on what you want to do, filling between curves, shading. Again, neat examples can always be fun. I like this one, being a quantum mechanics person myself, looking at basically the eigenfunctions for the harmonic oscillator in quantum mechanics and looking at the different levels of the wave function probability going through that. It's kind of neat. Options, you can look at any one of these things and see what's going on and get all sorts of different examples for what's going on. They may not always be fun to look at. This is giving me way too much of a flashback to GeoCities in my first web page 20 years ago as a high school student, when it was how gaudy can you make the colors possibly look. You can add labels, things to say, hey, look, it's an exponential function because, okay, great. Add legends. And this is a note, the legends, every time Mathematica comes out with a new release, I think it's on version 11 right now, maybe version 12, I haven't checked recently. This is something that keeps evolving, and I'm still not super satisfied with how Mathematica does legends, and I usually kludge my own in, but they seem to be coalescing on something that's at least workable. When I started using Mathematica 15, 20 years ago, legends were, well, I wouldn't say they were legendary. They were sort of legendary for being, please God, don't make me use those. Versus now they've actually sort of standardized it. You've got a bunch of options. Okay, so we're up to 12.2 now. Thanks. All right, so we'll flip back over to this. But so, you know, we could do things if you wanted to look at those options. So then all of those extra things you can always add as like extra arguments. I usually put them on a separate line just to keep myself reminded. But you can get like filling style and I don't know, let's say blue. That didn't do anything. How does this work? Because I don't remember how filling style works. So instead we're going to try something else. Let's do plot style. And so we're going to do green now, and notice we do that and it changes the functions that it's plotted in green. Cool. And we could add other ones to say, well, what if the aspect ratio, which usually defaults the golden ratio, is instead 1? Great, we can do things like that and it just changes how the plot looks. All right. Other things that we can do is, you know, depending on what the type of function is that we're looking to plot, we can also do parametric plots. Again, there's different functions for this to tell you sort of how telling Mathematica how you're planning to give the material. And so now you would actually put in a list for your function to say, well, we've got our x as a function of whatever our parameter is, y is a function of our parameter. And so, you know, to give us a really complicated example, we can look at the unit circle. So saying, you know, x is cosine t, y is sine of t, and now we specify the parameter and its value range going from 0 to 2 pi, and I accidentally hit the shift button at the same time. And we go and we plot, and out comes our circle. All right. If we wanted to do like a space curve or something like that, we can again have the parametric plot, but plotting in 3D is different than plotting in 2D in Mathematica. Not because plots are different in 3D than 2D, but because how Mathematica actually renders and treats two-dimensional graphics objects is different from how it treats three-dimensional graphics objects. So they're analog functions. If you've got plot for 2D, you've got plot 3D for 3D. If there's parametric plot for 2D, parametric plot 3D for doing things in 3 dimensions. You can convert between the two. That goes well beyond what I want to get into today, but we can do that. And so if you wanted to do, you know, turning our circle now into a solenoid, we can now add that z component in t, I don't know, maybe it goes up to 6 pi now. And just to show off also, if you don't like having pi, you can leave it as the capital P pi. You can also put in the symbol for pi and do that. And it gives you now this 3-dimensional thing where there's this frame and it looks really gaudy because the default options for plotting in 3 dimensions in Mathematica are terrible. But you can override those if you really need to. But the nice thing is, if you're really wanting to see what's going on, is you can now with the 3D graphics object sort of click that and drag it around and look at it from a different perspective and see what's going on and look and see, hey, look, there's our circle and there's the helix and what's going on. And sometimes that can give you a really good picture as to what's going on. If you want to ever combine a couple of graphics, which maybe you do, because you've got different things. So suppose we had our parametric plot. I'm going to copy this and bring it back down here. And we also wanted to show like a tangent line to it. So we've got our circle, we wanted a tangent line. Well, the tangent line, okay, we could make a parametric plot for it, but usually just y equals mx plus b is fine. What we could end up doing instead is saying, well, let's have a plot. And for our tangent line, you know, we get our derivative. So I'm going to do a little bit of a sophisticated, well, maybe not sophisticated, but just for time saving. So there's a block here called that you can have with width, which introduces sort of a temporary workspace where you can have a variable here. So let's make a function, let's call it f equals. And what we're going to do now is say it's a function. We can give it a variable, so it's only going to be one variable, call it x. And our function is going to be square root of 1 minus x squared. Okay, so it's the upper part of our circle. And so anywhere within this with block now, we've got f, and we can use that just as a function. We could have defined it at the global namespace, but I'm an old C++ person that says that unless I absolutely have a reason to define it in the global namespace, I won't. Because things get cluttered up, and then when I try to use f later, things get effed up. You're welcome for that joke, by the way. All right, so we want to plot, and let's do our tangent line, noticing that this is just the upper part of our circle. So we would do, well, our slope is going to be f prime. So our derivative, we could do derivative of f in this way if we wanted to. Another way is if you've got a function of one variable, Mathematica does recognize the shorthand where you can do f prime of x. Okay, but here we're going to want to evaluate it. Let's actually say at the point 1/2. So there's our slope times our independent variable plus, what would we have? What do we get here? So we'd have x minus 1/2, thinking back to our Taylor formula, plus now f of 1/2 itself, basically is a way of saying, how do we get that tangent line? And we would go in and say x goes from, I don't know, x goes from 0 to 1. Actually, let's make it -1 to 1. And so what we would now have if we try to do this is we're going to get a mesh. So notice that didn't actually superimpose the two. So first what Mathematica did was it did this with block with the plot and then the parametric plot. If we wanted to superimpose them, what we would do is there's this other graphics thing called show, where now it's going to go and everything inside this show function, you put the other closing bracket on there, is going to try to go and turn this sort of into an ad hoc list. We don't need the curly braces. You can specify them if you want, but you don't need them. And so now what Mathematica did was first evaluate that first plot, and then rather than just sort of sequentially showing them, it says now superimpose all of them together on the same set of axes. And we can see there's our circle, there's our line. The only downside, though, is that the axes that it will show go with whatever the first plot is. So notice we're missing sort of like, the bottom parts of the circle. If we flip the order, we could do that. Or we can use a lot of our graphics options. So you could try to do like things like plot range here for the overall show command to then try to recover the rest of that circle if you wanted to. Other thing, knowing that this sort of looks a little weird because the tangent line is the same color, is now it's where you can come in and say plot style goes to red, and now the circle's actually in red and the tangent line is in blue, and you can combine things and make more complicated examples if you want. I realize the tangent line to a circle is not something that's particularly exciting. So that sort of is a rundown of plotting. If we wanted to do plots of things a little bit more complicated, so like a function of several variables, you've got there's the plot 3D equivalent. So here's now where I'm actually going to make a function in global namespace, and we'll again give it f just to keep things confusing. So if we ever want to define a function in the namespace, so we can have whatever you want to call it. You have your independent variables, and the Mathematica syntax is you always have to end them with an underscore. So we have a variable called x. When we use it later, we're just going to call it x, but when it comes to actually declaring it here, there's the underscore. There are reasons for why that is that it's not worth going into right now, just that's what happens. You can use straight up equals to say define it now. Generally for simple things, using the colon equals, it's sort of as a delayed implementation, it works a little bit better. And I'm going to make a little function here. Something that's going to be maybe a little bit more sophisticated than what we had before, but that'll give us a nice plot. So we've got a function, and once we've done that, we can hit Shift Enter, and now f is defined. And notice it slightly changed the color of f to show us that it was defined. And so we can plot using this plot 3D f of x and y. And now we have to specify sort of what our values of x are and what our values of y are. And we can get this nice surface plot of what the function is doing. So we've got somewhere is our x-axis and our y-axis, and I don't know which one is x and y because they're both from -1 to 1. And I would presume this is x and that's y, but how can we know? Well, there's an option for that. We can add axes labels. And now, lo and behold, there's X and there's Y. And of course, that font is really small, and we could always change the style of the axes label. And now the font is much bigger. Okay, so there's all sorts of options that we can have to do that. But again, we can take this and we can drag it around and see that there's interesting things potentially going on. We can change the bounds if we wanted to zoom out a little bit and see that there's really some interesting stuff going on. So besides doing the surface plot, we can also do contour plots. And notice there's a contour plot and contour plot 3D. So if you actually want to look at contours of a three-dimensional function, so like f of x, y, and z equals a thing, this is how you do it, would be through that contour plot 3D, and that can be really nice, especially sketching surfaces blows. But here we just want to actually contour plot. And so we can do f of x and y. And so now what we do is, again, specify our range on x. And this one takes a little bit longer. And we get this nice little contour plot sort of showing us what's going on. The default color selection is gross. You can override that if you want. But we can see sort of, here's our different contours. If that wasn't enough detail, we can always add to the number of contours. I think it defaults to 10. So let's look at 50. It'll take it a minute to run, but we can start to see what's going on in all those contours. If you drag your mouse over, it'll tell you like there's the 0 contour, your 0.044. And so we can see now that we've got our maximum up there. We've got some minima off to the sides, another maximum, and this cute little saddle point there at the origin. But we can put all that together. One other nice thing for visualizing, you can tell I've spent too much time teaching Calc 3, is that there's actually another function, and again, both a 2D and a 3D variety, called region plot, if you want to try to look at a region. So the sort of the quintessential example that was is there's the bead where you take like a circle and you like bore out the cylinder from it, going between it. This is one of those classic problems. Well, Mathematica can handle this pretty nicely, and there's several ways to do it. So if you wanted to look at like a region that's inside a sphere of, let's say, radius 3. So notice we've got everything inside that sphere and outside the cylinder. So let's have our cylinder of radius 1 bored through it. Well, we can specify using the region. So there's one test. Are we inside the sphere? And are we outside that cylinder of radius 1? And we can use sort of the C++ Java-esque and ampersand for the logical and. If you also want to get pedantic, there's a function you can actually type in and with a capital A, square brackets, and then put the things in there. If you really wanted to get into functional programming. But we can do this, and we can then specify what are our bounds that we want. X, and for Y, and for Z. And we can see there's sort of our sphere on the outside, and there's that cute little hole between it, but that hole looks a little boxy. So again, this is one of those issues of resolution. This becomes increasingly important when you go to three-dimensional plotting, especially for things that aren't, rectangular, where Mathematica is going to basically evaluate things on a rectangular grid on a mesh, and you don't always get it as well as you would like. And so the way that you can try to work with the resolution is by looking at this thing of plot points. So I think it defaults to 10. You can check the documentation. We can go to 5 and actually degrade it to the point that, well, that doesn't even really look like a sphere at all. Or, increase this. And by the time you get to, 25, that's in each, I think the X, Y, and Z directions within our box here, this gives us a pretty good overview where now that actually looks a little bit more like the cylindrical hole going through that bead. But again, it's really helpful in my mind because you can actually take this, you can rotate it around and see sort of what's going on in the event you had a more complicated shape than this. But it's nice that, you can, I find it nice that you can just take sort of those inequalities and just shove them in there, and Mathematica will pretty much figure out what's going on in most cases. Questions? Like I said, so this is meant to partly be a tutorial, partly meant to work examples, but I also want to see some questions or see what are all of you thinking? Is everything clear as mud so far? All right, we're good. Okay, so I mean, I'll just continue along with some of the examples that I had in mind, just thinking of what are some operations that we might like to look at. And knowing that it's a computer algebra system, finding maxes and mins can be a nice thing sometimes. And one of the reasons why I actually defined this last function up here, this f, was this is a function. Notice we've got two maxes, two mins, and a saddle point. This is sort of one of those great Calc 3 examples for finding relative maxes and mins and saddle points. In fact, this is for both Nicole and Karthik, and I believe there's some other former students in the room. This was one of your homework problems. I grabbed this straight out of the textbook because it's such a great problem. Where this one algebraically is tedious because how do we go about finding the maxes and mins? Well, we would set the derivatives equal to 0. So let's talk about how we solve systems of equations or equations. So there is always in Mathematica, there's now a solve command, which says take some equations, solve them. One of the things here though is people, when they start using Mathematica, and I certainly fell into this trap when I was an undergrad, was that you think the solve function is sort of like omnipotent, and that it's like the God function because, oh my God, it can solve everything. And no, it can't. It's actually not as robust. There are some better things inside Mathematica and more robust things. Take a look at the reduce command if you get anything really weird. Solve is great if you've got polynomial equations or things that are relatively simple. If trig functions come up at all, good luck with the solve command. Just, you've been warned. But anyway, for doing this, so you can come in and say, well, let's say you had your function, I don't know, so let's say x squared minus 1 equals 0. And of course, there's the C++ sort of equals for being logical equals. The regular, just like a single equal sign, is going to be like an assignment operator. So again, make sure when you're doing this, you're using the Boolean equals, the equals construct in there. And so you could say solve x squared minus 1 equals 0, and you need to tell Mathematica what variable do you want it to solve for. In some cases, it's fairly clear, but you can still do that. And notice it comes back, and here's where you see now the list framework. So it says, well, there's a list, and then within that, there's another list telling you x goes to -1. It doesn't tell you x equals -1, it says x goes to -1. And there are some pedantic reasons for why Mathematica does that. By the way, the reasons for why does Mathematica do anything, it's pedantic. If you ever want to know why, go read Stephen Wolfram's book, the Meaning of Everything, or whatever it's called. It's this big tome book, just to show exactly, oh, this is being recorded. I'm going to delete the comment I was about to say. Stephen Wolfram has a very high opinion of himself. Okay, so anyway, we can do that solve. And so if we wanted to find relative extrema, well, then of course, what we would do is set up a system. So we can now bring in a curly brace. So we've got a list where we can put as each item in our list, all of the equations in our system of equations. And we want our partial derivative of f. So we've got our function f of x and y, partial derivative with respect to x. We want that to equal 0. And we've got a partial derivative now of x and y with respect to y to equal 0. And now we're solving, with respect to x and y, and we can plug that in. Mathematica gives some warnings. Notice these aren't errors, but just saying, basically it's reminding here, oh, you've got a transcendental function. You've got an e to the something or other. Just be warned. It's sort of telling you like, solve's not guaranteed in this case. Use your results as you will. Anyway, everything's fine. And it turns out in this case, it finds there's all 5 of the critical points that we were able to actually see up here on the contour plot. And so this tells us the locations of those. And of course, we could then plug those into F. We could program a second derivative test if we wanted to then determine, what's going on. There are other functions inside Mathematica. So there actually is a minimize function. Likewise, there's a maximize function. The downside, though, is that they're not always all that useful. And so, for instance, if we come in here and we try to actually give it our function, f of x and y, and we have to tell it again, what are the variables that we're minimizing over? Wow, that was helpful. So we go to evaluate it in Mathematica, other than it plugged in f and said, well, f isn't some function, it's the, this 1/2 minus x squared plus y squared times this exponential thing. The issue is that the built-in minimize and maximize Mathematica functions, this is actually described in the documentation, say it's only guaranteed to really work for polynomials. And so Mathematica went in here and said, oh, you didn't give me a polynomial. I don't know what to do. And so it didn't even try. It just returned it to saying, well, the value of minimize of f of x and y with respect to x and y is equal to the value of minimize of f of x and y with respect to x and y. Mathematica loves its syllogisms. Now, that being said, part of the reason is because it doesn't know, without this being a polynomial function, you're not guaranteed to have a minimum. Okay. And so one of the things that you can do is actually add a constraint. If you make this into a closed domain now, that should actually be a curly brace, not a square brace, and say, you know, let's make it x squared plus y squared. So we're in the unit disk. Now, so we've got a closed domain. Now, with a closed domain, you have your extreme value theorem. It's a continuous function. And now there actually is a minimum value. It's guaranteed. And now Mathematica will actually try to go and find it. And sure enough, it tells you that your minimum value is -1/2. And it gives you the location of occurring at x is -1 and y is 0. If you wanted to extract those, you know, this is now where you can get into parts of a list. So what number is that? That's out of 85. So I got one into the Zoom chat bar. Out of 85. If you want to get like a part of a list, so to actually get that minimum value, there's a function you can invoke called part. The other shorthand for doing that is to use double square brackets, because that doesn't get confusing when you start chaining these functions together and you now need to start doing parts of lists. And suddenly there's like 15 square brackets all floating around because cool. Right, but you can do that and that'll just pull out that -1/2 if you needed to actually access that. If you wanted to get the actual x value of -1, well, you would start by saying, well, it's the second part of that, but notice that now just gives you that total list. So you can change together, well, it's the first part of the second part of the list, and the actual value is now the second part of that. And so you can start chaining all of that together. And this is where list operations become really critical, because all of these return values for even fairly simple functions like minimize, Mathematica is going to put everything in a list for you, and sort of, you know, pulling out the items that you want is sort of like banging your head into a desk. Again, it's not so much as learning how to program in Mathematica so much as learning to ask the question it wants to answer. Okay. So that's sort of like, again, sort of more sophisticated built-in machinery, but there are these, you can do numerical root finding as well as maximum and minimization. Again, just sort of put the capital N in front of it. Although with it being a numerical method, it won't do it symbolically. So having to provide a starting guess, so find, you know, what's the minimum closest to x equals 5 or 2.5. You know, you'll have to do that, but you can do that. That functionality is built in and it works pretty well. In most cases, it's not always the fastest. In some cases, this one, it might actually be competitive with MATLAB, because Mathematica will do the derivatives probably a little bit better than MATLAB would symbolically. But you can do those options too. Yeah, and yeah, the N solve. So a lot of these functions, like we saw with the integrate, you can put a capital N in front of them and it'll just automatically do it numerically. If there's any sort of symbolic work going on underneath the hood, Mathematica is usually pretty sophisticated in that. And so there's also stuff. If we want to turn to like linear algebra concepts, matrices, I mean, you can do it. This is where if you're really wanting to do linear algebra and matrix analysis, what you're probably thinking is, I should be using MATLAB. And unless you just really have like a symbolic matrix, where you're not actually providing numbers, like you've built some model and there's parameters in your matrix, so it's actually a function of these parameters, what you probably want MATLAB. But if you wanted to do matrices in Mathematica, well, a matrix is just a list of lists. So you could have, you know, here's some A11, some A12 element, A21, A22. There's a 2x2 matrix as a list of lists. If you wanted to view it in a different way, you can always change your output. So you can either put this in matrix form with square brackets around it, or change the output at the end with that double slash, and see that we can turn that into a matrix. Noticing now that Mathematica will give you the results in row major format. So those of you that are used to like C or C++, have fun. Those of you that are used to Fortran, well, it's already in row major, but you shouldn't be using Fortran. There you go. And so you can do all sorts of things, but there's lots of different things built in. So if you wanted to do row reduction, you notice there's a function, row reduce, plug in your matrix. You had one called M, square bracket, M, done. We could say M equals that, although we'd want to get rid of the matrix form. Do that. You can row reduce M, and lo and behold, here it gives you 0, 1, 0, 0, 1, because it assumes those are all different values. Yay. Suppose we want to do something a little bit weirder. So we want to do actually like an eigenvalue analysis. Depending on what you want, there's several different things. So if you just want the eigenvalues and don't care about the eigenvectors, you can just do eigenvalues. If you don't want the eigenvalues and only want the eigenvectors, you can just call eigenvectors. And if you want both, there's the function eigensystem. And so notice it'll try to do it symbolically here. And this is a small enough matrix that it will succeed. And so the first thing it does, again, here's like lists, and now here's where the lists get really weird, because now there's sort of two lists, but then one of them should be an eigenvector matrix and one is eigenvalues. In this case, it returns the first list is the eigenvalues. And so we can pull that out. And the second one is actually the eigenvector matrix. But the problem is what it's doing is it's listing. So then this first list is the first eigenvector, followed by the second eigenvector. So it's actually the transpose of the eigenvector matrix, because it's giving it to you in rows, not in columns. And so this is where, when you're trying to do this style of analysis, all of a sudden you're like, wait a second, is this the transpose? Is it not the transpose? And all of a sudden you're beating your head against the desk. So just be careful if you're doing these types of operations that you've got the right form and you're working with the list correctly, because it can get weird. But other things, I mean, Mathematica, you've got singular value decompositions are built in. You've got QR decompositions. You've got LU decompositions. If you want to do matrix functions, so you've got other things, so like matrix power. If you wanted to calculate like A times A times A times A, however many times out there, you can do M to the, 24th power. And we can, look, Mathematica will do it completely symbolically. Look at all of this page after page of page of algebra showing you exactly what that little 2x2 matrix was to the 24th power, in case you were ever curious. I wasn't. All right, you can also have, for differential equations, there's also the matrix exponential built in. There's the matrix logarithm, all sorts of different functions if you want to do matrix operations. But again, in most cases, you probably have an actual like numerical values for the matrix, and MATLAB is going to be better at this than Mathematica, at least in terms of efficiency and time to solution, once you go numerical. Questions on any of that? So I thought maybe the last thing we could look at, because this is where symbolic work can actually be a little bit useful, is actually looking at some differential equations. Mathematica certainly can do differential equations, and it will do them symbolically as best as it can. And I should also specify, like when it came to doing like integrals earlier, when we did like antiderivatives or even just definite integrals, it's not constrained to doing fundamental theorem of calculus type things. If you've got actual like integrals in the complex plane, Mathematica has no trouble using like the Cauchy integral theorem. It's got a whole bunch of tools built in for doing this. If you want to know how did Mathematica actually go about evaluating that integral, don't peek behind the curtain. The wizard is not seeing visitors today, but it will do it. And you can do a whole bunch of analytical integral evaluation, even if they're not things that fundamental theorem of calculus would necessarily work with. There's all sorts of other tools and other sorts of neat things built under the hood. That integral engine is really quite powerful. And so, one of the things that you can start to do is, like you've got solve, there's also then a dsolve function for differential equation solve. And so you could put together, some sort of equation now. So you'd have, well, if we have just an ordinary differential equation, so some function x is a function of t, and this is equal to, r minus, so r is a constant, k times x is a function of t, so some inhomogeneous linear first order differential equation. Just like with the solve, what are we solving for? In this case, it's the function x of t, and we have to tell Mathematica what the independent variable is as well. But we can plug all that together. And again, there in our list format tells us, well, your function is going to be x of t is r over k plus, there it is, up to, notice we've got our constant of integration, essentially, because we didn't actually specify what the initial condition was. Those of you that are curious, I took this example from the differential equations book I used a long time ago in undergrad. I think this book is still out there. This was the 7th edition, so they're probably on at least the 12th or the 13th right now, because otherwise Brooks Cole hasn't made enough money recently. But this was basically the rate at which a drug disseminates into the bloodstream is governed by this differential equation where R and K are positive constants. Doesn't even tell you what they represent. Cool. The function x of t describes the concentration of the drug in the bloodstream at time t. Great. So we've got concentration of drug in bloodstream. Maybe it's the concentration of COVID vaccine, and hooray, I've got mine scheduled for Saturday. I'm excited. All right. So, but you can do that. If you wanted to actually specify the initial condition, you can then say, well, that's another equation that we've got. So we can put in sort of the list there and say that, I don't know, x of 0 is equal to, again, using our double equals, and was equal to 1. I don't know, I just plugged in a number, and notice now that constant of integration is gone, and it went ahead and solved for what was the appropriate value of C and put that in. Other thing that can sometimes be useful, I'm not sure it'll make a difference in this particular example, but sometimes the algebraic results that Mathematica spits out, so things sort of like up here, get a little bit unwieldy, and sometimes that's just the nature of the result, but sometimes that's because Mathematica was feeling a little bit lazy. And we can throw in, there's a simplify command to say, try to clean that up a little bit. Okay, here it didn't really do anything. And in some cases, that's not enough. There's then the full power one of full simplify. And this is a simple equation, it didn't do anything. But if you want to try to clean things up, there's the simplify, full simplify. There was one, I don't remember if this one is still a thing. No, it's not. So there used to be one called trig simplify. If you had a bunch of trig functions that would explicitly try to deal with trig things. But I think they just folded that into full simplify back around, I think, Mathematica 7 or 8. When I started using Mathematica, it was on version 4. So excuse me if some of the old tricks that I'm used to are no longer relevant. I forget where they got deprecated along the way. But if you're ever dealing with the symbolic stuff, that simplify command can be an absolute lifesaver. You can also specify, again, you can see in the documentation how to do this. But if you know certain things about your variables, so let's say we know that K is a positive constant or that R is a real number, you can specify that to simplify rather than just assuming that it's an arbitrary real number or it's a complex number or things like that. You can add that information and then simplify will take that into account when it tries to simplify. So the more information you can give Mathematica, the more it can do for you in those regards. Okay, so thinking back to the system of equations, are there limitations for solving a system for a bunch of differential equations? Would it be useful finding complicated system steady states? So, I mean, are there limitations for solving a system for a bunch of differential equations? Yeah, how much memory do you have on your computer and how long are you willing to wait? You can plug in as many into Mathematica as you want. The issue just is, keep in mind, is a symbolic solution going to be helpful? If it's not, because I mean, the other thing to keep in mind is the bigger you make the system, even if a symbolic solution is feasible, it may not be particularly instructive, because if you've got like 100 by 100, or 100 system of 100 differential equations together, that's 100 unknowns. You could maybe write that down symbolically, but are you going to gain any insight from it? And the answer is probably not. And so there's sort of the limiting, the trade-off of values in that. But then more than that, you're probably going to just do it numerically at that point. And I'm not sure Mathematica would be the best thing. Again, I'm not sure MATLAB, when it comes, Oliver could probably speak to this better than I could. I'm not sure how good MATLAB is at doing differential equations. I'm pretty sure it's decent for doing numerical things, but I'm not sure how it compares to Mathematica in that sense. I know if we're doing just like matrix vector operations, MATLAB will smoke Mathematica. But for doing some of the differential equations, especially if they're complicated or nonlinear, I'm not sure. The other thing is Mathematica might try to do it symbolically under the hood and then just plug in the numerical values at the end, versus MATLAB will probably just try to do it numerically from the outset. So if you've got some sort of like stiff differential equation, MATLAB might get stymied depending on what's going on. And I actually have a system of differential equations to look at a little bit later. If you're just looking for, steady states and the system of differential equations, if it's, first order, linear, and everything's homogeneous, then what you're really just looking for in that sense is, figure out what the coefficient matrix is. And rather than thinking about it as differential equations, just look at the eigenvalues of that coefficient matrix and say, well, what's the zero eigenvalue and what are the vectors associated with it? And that might be an easier way to do it. And in that linear algebra sense, MATLAB would probably be the better sense to go, because you're going to get a reasonable size matrix and you just want to know what are the eigenvalues and eigenvectors. Mathematica can certainly do it. Just MATLAB would probably do it faster. Does that answer your question? In a very long and verbose and roundabout way. So the other thing though is that was a sort of cheesy example, but it's nice that Mathematica can also do, much higher order differential equations. So if we wanted to have, just as an example, and just as a note, capital E is the exponential. You can do it as exp as a function or just capital E. And so we've got also our cosine function. We can solve now for y of x, and x was our independent variable, and it can chug away on that. We can see there's our three constants of integration, our C1, our C2, and our C3. And again, we could specify some sort of boundary or initial conditions to do all of that. I like this problem because it's now inhomogeneous, it's higher order. Again, showing that if you don't want to have to think about the variation of parameters, because like hell, I remember what that is. There's a reason I don't teach Cup 4. I don't have to. Mathematica just knows how to do it, and there's the solution. Because realistically, when I'm doing research or working on problems, I don't really care how you go about solving the ODE. I just want to know what the answer is. And Mathematica is very good at accomplishing that. Yes, I could always look up what variation of parameters was. I don't care. All right. So I actually had Karthik a system of differential equations prepared for you. So you can also sort of bring in a D-solve. And so now again, we've got a system, so we're gonna have to bring in our list notation. For now we have, let's say, x prime of our independent variable t equal to 3x of t minus, let's say we've got another function for y, and let's make it inhomogeneous just because I'm feeling thrifty. Specify y as a function of t. Close our list. And now what we're going to do is we have to specify what we're solving. We've got x of t and y of t, and t is still our independent variable. And it can come in and it can solve that and say, well, there's x, and there's a thing, and there's all of our constants of integration floating out at the back end. There's what y is. Again, if you wanted more insight into this, this is not, to me, a particularly useful expression. Maybe you needed that analytical result. That's great. This is starting to get on the sense of what's going on. You'd probably just do an eigenvalue analysis here and see what's going on. And this is 2 by 2 Mathematica could chug that. You're not going to see a noticeable difference between Mathematica and MATLAB, but there might be other styles of investigation you would want to do rather than actually getting the symbolic results. The other thing that you can do is also always add those initial conditions. So we can add more equations here to say like x of 0 is equal to, let's say, 1, and y of 0 is equal to 0. And then now we get something that's a little bit simpler, because we can eliminate all those constants of integration, but we can also build all of that information into that D-solve when it goes in to do it. Other things for dealing with like systems of ODEs and whatnot, and talking about, integrals, you can do Laplace transforms in Mathematica. Again, this is built in, so if you want to do Laplace transform, sine of kt, first thing you do is specify, well, what's the variable that you're getting rid of, and what do you want to call the new one? So we're going to go from t space to s space, and sure enough, the Laplace transform of sine of kt would give us the k over k squared plus s squared. Those usually aren't too bad. The one that's a little bit more fun, inverse Laplace transform. Okay, trivia question for our fun factoid. What is the name of the integral that you're evaluating when you want to try to do the inverse Laplace transform? Hint, I am not looking for the, oh, it's the inverse Laplace transform integral. It actually has a name to it. Does anybody know what it is? While I type in our function. And we specify now where S was our Laplace parameter, T is what we want to go back to, and sure enough, we can get back to sine of KT. All right, do we have any guesses on the name of the integral that the inverse Laplace transform is evaluating? If you were thinking, but too shy to type in, the Bromwich integral, you are correct. You're awesome. Okay, but sure enough, I mean, that integral is annoying to say the least. And so the good news is, Mathematica, you can invoke all of that integration machinery through the inverse Laplace transform function, and it'll just do it for you. Again, depending on how complicated the expression, this could take a long time. You might want to, set it up right before you go to bed, hit Shift Enter, and just let it run overnight. That was some of my doctoral thesis. Many nights did my computer spend time doing that. But then other integral transforms, if you want to do like Fourier transform, again, those are built in to Mathematica. There's similar functions like this. You can do, if you get into a lot of complex analysis, the Hilbert transform is built in and can be quite useful. Again, whole bunch of different transforms that are available and doing integral analysis and things like that. And maybe, I guess we're coming up on sort of the end here. I guess I'll pause. Just, does anybody come up with any other questions or comments or thoughts they'd like to share? I've got a short example for just, we can do some PDEs as well in Mathematica, at least when they're simple. I mean, most PDEs, just analytical solutions, aren't even feasible. And in that sense, I would not recommend Mathematica for doing numerical PDE work. But if you've got a simple enough PDE or just want to sort of prototype things and can do it symbolically, Mathematica can be a really convenient engine to do a few things. When I took PDEs as an undergrad, the professor said, if you're in reality, this is a symbolic PDEs course and you learn a lot of the fundamentals, but in practice, if you're working with a PDE that has a symbolic answer, you're studying a boring problem. And that's just sort of where things are at, but okay. So you've heard Mathematica is often used in finance. That wouldn't surprise me. I can't speak to that myself personally. I've never worked in finance. But I do know, yeah, my guess is, because I know stochastic differential equations, a lot of the Ito calculus is implemented in Mathematica. And so it provides, there's so much implemented in Mathematica. That so if you want to do any sort of like non-standard operations, it may not always be the most efficient for doing them, but compared to it being kludged into things like MATLAB or having to use a completely standalone or piece of software and then string different pieces together, Mathematica can provide a really convenient sandbox for doing a lot of very disparate and unrelated operations. And that would be my guess. Yeah, some of that could also be that Robert Fry is just a big Mathematica fan. I mean, it's one of those, to me, like when I do examples in Calc 3 and in 510 and all that, it's usually Mathematica, not because Mathematica is the best, but because this is what I'm expert in. And when I had all of 5 minutes to jury rig that example together, this is what happened because I didn't have to Google a bunch of shit to make it happen. I don't know. I don't want to speak for Professor Fry when saying that he's a Mathematica fanboy, but I do know he does like Mathematica. All right. So anyway, the nice thing about PDEs is that it's the same sort of command. It's still just dsolve for differential. There is the ndsolve for doing it numerically, but like I said, I wouldn't really recommend Mathematica for doing numerical differential equations unless there's just unless you're just, everything else is already in Mathematica and it's just a convenient way. They're better tools. But if you wanted to look at, how would this work, we can actually add partial derivatives. The downside, though, is there's no easy way to do partial derivatives. There's no shorthand in Mathematica. Like you had the prime symbol when you had a function of one variable. So this gets to be a little bit kludgy. We have to actually bring in our d. So there's x. Notice there is now a space between the x and the d. So x is going to be our independent variable. If there wasn't that space, Mathematica would interpret as that is the symbol xd. And it'd say, I can't find the function xd. It's not defined. Make sure there's that space to let it know that you've got x and d. The function now. So we could take we've got our function because differential equations and PDE switches over to u because why not? So let's have x times the partial derivative with respect to u plus y times, again, there's a space, u of x and y. So we have our partial derivative with respect to x, and that's going to equal -4x space indicating times y space indicating times u of x and y. We'll leave that as just one equation for now. And we can then say, well, what's our dependent variable? That's u of x and y. And our dependent variables, now again, we need to bring in the list. There's multiple ones to specify x and y. And Mathematica will come back and then up to our constant of integration, show us, well, there's the answer. It was actually able to solve that one symbolically. And then if we wanted to add an initial condition, we've already got the list here, so we can bring that in. So let's say we've got u of x and 0 is now equal to, and we've got a function exponential of minus x squared. Input that in, and notice now it gets rid of that constant of integration. Will just give us our e to the negative x squared minus y squared being the solution. And of course, we could plug that back in and validate that solves our PDE. That's about it for the examples that I had worked up, which seems like I had about the right number of examples for the time frame we had in mind. Just to comment that beyond this, so yeah, like things we mentioned, Ito calculus and stochastic calculus is also Mathematica. There are also lots of tools for doing probability and statistics. A whole bunch of different probability distributions are built in. If you want to look at probability density functions, cumulative distribution functions, all sorts of moments, there's a lot of tools in Mathematica to help understand this, again, in a symbolic fashion. And I've made use of them from time to time. There's also quite a bit for graph theory and discrete math within Mathematica as well that I am not as proficient in, because it's not something that I've typically had to work with a lot. But they're there, and the documentation is pretty helpful when it comes to that. But so sort of if you're looking for like a one-stop shopping to start doing prototyping on things where you need to do some symbolic work or don't necessarily want to go into full numerical effort, Mathematica can usually provide a pretty good way of doing that prototyping without a lot of overhead and a lot of baggage, because so many of the tools and the techniques are built in, and you can then sort of string them all together all in this sort of same notebook and same format, and start doing visualization and data analysis to help start to build some intuition for what's going on. But then knowing that, you know, in that sense, Mathematica is sort of the jack of all trades, master of none in that regard. When you really want to start going into production runs and go to things beyond prototyping, unless you're actually just doing symbolic calculations, Mathematica is probably not the best piece of software in that sense. And you want to move to something a little bit more specialized for what the rate limiting step is for the exact problem you're trying to solve. Okay. That's all I've got prepared. I know we've got a couple minutes left here for questions. I know you've been sort of asking them throughout or interjecting them, but just, you know, open up the floor for, I guess, general discussion. Thanks everyone so much for coming and letting me bore you for 90 minutes. Can you run Mathematica from the terminal? You can, yes. So there are ways to invoke a Mathematica kernel from the terminal and then feed it in. I have done it in the past. I have not done it recently. So I don't want to comment any more on how to do that because it might have changed. It's been probably 6 or 7 years since I've done that. But that is a thing. When I installed the most recent version of Mathematica on my computer, there was actually a dedicated script that came with it. Rather than opening up the Mathematica notebook front end, there was like a Wolfram command or something. I don't remember what it was called. I've never actually touched it. But yes, you can run Mathematica from the terminal, which can be a little bit nicer if you actually try to like edit code. These notebook styles aren't always the best. And when I've had actually like doing functional and programming in Mathematica to actually like put my code in a sub file and then I would actually run that individually, yes, you can do that. Any suggestions for beautifying them? Changing the color scheme? You know, you could look at the different options. Usually like just the default, like the frame I think is ugly depending on what you want. So you can like turn the frame on and off depending on how you want to plot it. You can change the colors, whether you want axes or not. The color scheme mostly to me is, I just think the default color scheme is ugly and you can change it. I forget what the option is. So let's go back up to our plot here. its color function. And so you can choose different ones here. And again, you can look in the documentation for what are options, but you can change the color function and get, you know, different things. And I mean, that to me looks a little bit nicer just because the color scheme isn't awful. Sometimes you want the actual mesh to see sort of what those level curves are along there, but you can actually turn that to be, you can turn that off to actually just get the surface itself. As a follow-up on Oliver's question, can any mathematics take advantage of parallel processing or other parallelized analogs? So my understanding, I've never done a lot of work with parallel Mathematica. My understanding is that more depends on your license of Mathematica than the actual functions themselves. I believe underneath the hood, they are programmed at least as much as possible to make use of that, but it depends on the license that you've acquired. So like I know on my computer, I believe I have just a single license or a single, you know, processor license. It's possible, no, it's a single computer license. It might run on multiple cores, but to actually try to do like, you know, thinking like the MPI style across different processors, I think it would depend on the licensing, and I'm not actually sure off the top of my head. I've never done anything sophisticated. Again, if you're going to go to that level of processing, my advice would be probably to try to find a more specialized piece of software that'll be more efficient. You're sort of moving beyond the prototyping if that's really what you're getting into in most cases. Yeah, Mathematica is sort of closed source. You can always do your own programming in Mathematica. As I said at the outset, it is its own language, but then how does Mathematica work behind the scenes? Black box. And the wizard is not seeing visitors today. You don't get a heart, you don't get a brain, and you don't get courage. Wah, wah. All right. Other questions or comments? Otherwise, it's on 1 o'clock. I know some of you probably have other places you need to be. Yes, there is always Octave. I've never played with it, but it's one of those things that with an infinite amount of time, I would love to experiment with Octave. Right. Well, thank you everyone for coming and for joining us today. I hope you found this either helpful, insightful, or entertaining, or some combination thereof. And I'll turn everything back over to Karthik to wrap up.
Awesome. Thank you so much, Matt. This is a great talk. And yeah, that's it. Thank you.
My pleasure. Have a great day, everyone.